Example 2. A rectangle has one corner on the graph of y equals 36 minus x squared, another at the origin, a third on the positive y-axis, and a fourth on the positive x-axis. So we're given a picture. So first let's recall a y equals 36 minus x squared graph is a parabola. Because it has a negative x squared coefficient, it's going to open down like this here. And we can see that the 36 is going to tell us its vertex is up at 36. So here's an approximate sketch of that piece of that parabola. So one corner of our rectangle is going to be on this graph. So right now it's drawn here. Now, as we would trace along this graph, like let's say I move to a point up here, my rectangle would become taller and thinner. So you can see that this is going to change as we move along the graph. If I came way up here, it'd be super tall and thin. So that's the idea, is as we move along this graph, that rectangle is going to change size and shape. Okay, so the fixed point here is at the origin, so this one has to be here. This one could move. This one has to stay at the origin. The third is on the positive y-axis, so one has to be here on the y-axis. And again, as we trace along this parabola, that would slide up or down. And then the fourth has to be on the positive x-axis. So again, as we trace along this parabola, if this rectangle got taller and skinnier, this x value would slide in. Part A, we want to express the area of the rectangle as a function of x. So first let's recall our area formula for rectangles. So area is equal to the length times the width of the rectangle. So as it's drawn here, our length and width, because this is tracing along this parabola, are actually going to be the x and y values, of that point. So we can substitute in for L and W, x and y. Now we know that if we want area as a function of x, we want a of x. So then we want the only variable besides a to be x. So we've got to substitute in for this y. But we know that anywhere we go on this parabola, the y value is going to equal 36 minus x squared. So I'm going to substitute in, instead of y, 36 minus x squared. So right now we have a of x. So we could leave it like this, or we could multiply and simplify, rearrange the terms in descending order. Not necessary, but sometimes we like to do that. So we distribute and rearrange it. We get negative x cubed plus 36x. So this is our area as a function of x. Part B, what is the domain of A? Okay, so we know our domain, our function, talks about area. And to get this area, we have x and y values on this graph, on this parabola. So when we're talking about the domain, first we know that our x value here has to be positive because x represents the side of that rectangle. So we know x has to be positive. Now we also know, so the x, if that represents the length, then this 36 minus x squared represents the width. Well, we know that would also have to be positive. Both the length and the width, both pieces that we multiply to make up that area have to be positive. So not only does x have to be positive, 36 minus x squared has to be positive. So if I solve this inequality by adding x squared to both sides, I get 36 is greater than x squared, and then if I turn that around, x squared is less than 36. Now we could formally solve this by making a sign chart, but informally we can just eye this and see that we want to think of x values that when you square them remain less than 36. So just pretend what x values would equal. What x values would you square to equal 36 when we know we'd square 6 to equal 36? So we could get anything up to 6, like 1, 2, 3, 4, 5, right up to 6, not including 6. But since we're squaring, we could also go down negative as well. So we could go down negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. So we can see then that the x values here, any x values between negative 6 and 6, would satisfy that inequality. So if we want to see where these two overlap, so our domain has to satisfy x has to be positive and x has to be between -6 and 6. Well, these two inequalities would overlap between 0 and 6. So our domain is 0 to 6. Part C, graph a equals a of x, and find for what value of x a is largest. So let's get our graphing calculators here, and we enter our function, -x cubed plus 36x. Now, when we enter our function here, we always want to think about a reasonable viewing window, and our reasonable viewing window is our domain, essentially, in this question. We already talked about the domain. So we know on the x-axis, we're going to go between 0 and 6. But let's think about reasonable values for our y-axis. So in this function, the y value, the a of x, is area. So we know area has to be positive. But how high do we go? Well, we kind of guess and check here and see until we get an approximate shape in the viewing window. Or let's look at the table. So we know our x values have to be positive and up to 6. We know those for sure. We just found that in part B. So if we look at the table where x is between 0 and 6, if we eye these y values, the highest one I see is in the 80s. So let's just ballpark it and go a little bit higher. It's always best to go just slightly outside the viewing window to get the best shape. So I'm going to go on my y-axis from 0 to about 90. So my window, 0 to 6, because you found the domain in part B. And then my y-axis here, my y-min and y-max, again, y is area. Area has to be positive. And those y values look like they go up into the 80s, so I'll just go a little higher to 90. Now note, once you increase the range of either the y values or the x values, you want to increase the scale. So if I left the scale as 1, I'm going to have 90 tick marks on the axes, which would kind of blur together and look like one big fat line. So I increased the scale to 10. Just an example, doesn't have to be exactly 10. So I graph, and I get this approximate shape here. So I would make a little sketch in your notes. So let's make a little sketch so we have that to refer to. Again, just the approximate shape's all we need. So now we want to find for what value of x a is largest. So I can see it looks like I've got a max up here. And so we just want to calculate the x value at that max. So we'll do our second trace to calculate our maximum value for, so option 4. And so we want a left boundary. That actually looks fine the way mine defaulted there. I'll hit enter. And then either cursor over, arrow over, or type an x value. Type enter. So I've got my arrows here. And then I can move my cursor close to where that max looks like it appears. And hit enter one more time. And I see that my max is about 83, and it occurs at an x value of about 3.46, etc. So I'll just round this to 3.5. Again, pay attention in my math lab or on a quiz or a test to how they want us to round. So I can label, let's label our picture, 3.5, comma, 83.1, just approximately. And it's also useful when you use the graphing calculator in notes to make a sketch of the viewing window that you used. So this notation may be new to you. You may have seen it in a previous class. We use brackets and we say x min, x max, x scale. So our x values, we went from 0 to 6 in our window, and we had a scale of 1. And then we do our x here for by, like the dimensions, the x values by the y values. And then we make brackets for the y values. Remember, our y values went from 0 to 90, and I changed the scale to 10. So it's always useful, I'll try to remember to tell you in our notes, to sketch these. So if you want to go back and check this, you can see the viewing window that we chose. So our answer to this question then, for what value of x is a largest, x is approximately 3.5.